Hi, I'm Arden Knoll. I'm a student at Michigan State University, and today I'll share with you our work on fast developmental stereo-disparity detectors. By the end of this talk, you'll see how developmental networks can be robust, real-time solutions to current stereo-disparity detection problems. You will understand their inner logic and see how they can be applied to accomplish stereo-disparity detection tasks through a practical example. Traditional stereo-disparity detection methods use some form of matching between small image patches in the left and right images. However, problems arise when the image patches have weak texture, meaning all the pixels in the patch have nearly the same RGB value. This results in many different disparity values indicating a strong match. Furthermore, since symbolic methods use handcrafted features, they cannot handle complex distortions provided in real-world binocular images, such as the differences in viewing angles between each camera, any shadows or lighting differences between the cameras, and the inclusion of objects in one camera's image that have not been included in the other. Because of these problems, symbolic systems tend to be brittle and perform poorly in natural settings. So how can we do better? What if we learn the features instead of handcrafting them? This would make our system much more flexible, because our system can learn the complex rules of the physical world instead of relying on a simplified world model. However, connectionist methods tend to require more computations and take time to learn, and act as black boxes where decisions made by the system are not easily explained. Developmental networks can give us the best of both worlds. DNs are general purpose and thus highly adaptable. And while they must take time to learn, they learn optimally throughout a single lifetime and follow clear and explainable logic. A predecessor of the DN was tested on stereo-disparity detection in the past and was able to attain sub-pixel accuracy on simulated binocular images where the monocular images were shifted horizontally. In this project, we extended the past work to develop the first developmental stereo-disparity detection system on real-world binocular images. We also developed methods to better handle weak textures. With volume dimension, we add a dimension to each neuron's input vector that signifies weak texture by taking a large value when the other entries have low absolute values. For subwindow voting, we group the neurons into competition zones that share the same input. The neurons compete against each other, and the winners of each group get to vote for which motor neurons should fire next. For this project, we used Genisama's VCML100 hardware, along with a Sony Xperia G8142 phone running on the Android operating system. We designed and built an Android application called 3DI to run and interact with the DN for stereo vision tasks. When we designed this application, we had to keep in mind three mutually conflicting constraints. We wanted to hit real-time speed while minimizing costs and increasing mobility, all while maximizing accuracy and precision of the DN's responses with the end goal of helping a blind person navigate their environment safely. Our choice in hardware allowed us to hit the cost and mobility constraints, but it limited the computational power and memory that we had available for the software. Because of this, we had to make a few decisions on our DN's architecture. There is a trade-off between the number of neurons available and the size of the input for each neuron. Because of this, we limited the input region to a 135 by 135 pixel mask on each image. We divided the mask into 9 non-overlapping subwindows and grouped the hidden neurons into 9 distinct competition zones, or columns, the neurons in each group sharing the same subwindow as bottom-up input. It would be beneficial to increase the number of subwindows and the size of the mask, but the number of hidden neurons allowed given the memory available was the limiting factor that led us to these parameters. Because the DN algorithm is highly parallelizable, we designed a more optimal version using the GPU and multiple CPU cores to help achieve real-time speeds. So how does the DN actually work? We first initialize the X, Y, and Z areas with K+1 neurons in each column in the Y area. We compute each neuron's pre-response by taking the dot products between input vectors and weight vectors and adding the results. Each neuron has 3 weight vectors, one for bottom-up connections, one for lateral connections, and one for top-down connections. For this work, we did not use lateral connections and weighed the results of the top-down and bottom-up computations unevenly. To perform the top K competition, we find the K neurons with the best pre-responses for each column and scaled the responses based on how close they were to the K+1th neuron's pre-response. Every other neuron not in the top K has its response set to 0. The winning neurons update their weights according to our Hebbian learning rule. The motor neurons use the entire list of hidden neurons as their input vector and follow the same procedure. The exact equations can be found in the paper. So how does the DN perform stereo-disparity detection? What actually occurs under the hood? Let's first look at the bottom-up weights of hidden neurons. As the neurons learn, they strengthen and weaken different weights, where consistent patterns are strengthened and noise is averaged out over time. If you look at the rightmost column of this table, you can see what happens to a neuron's bottom-up weights as it's updated through time. The part that is strengthened is the pattern tuned by this neuron, and the shift of this pattern is the disparity tuned by this neuron. This implies a very important result, that the disparity information is embedded within the binocular pattern itself. The DN learns to extract the disparity information from the patterns it receives by firing the hidden neurons whose bottom-up weights best match the input pattern, thus matching the pattern's disparity as well. The motor neurons then take the hidden neuron output to decide the final DN response. Generally, a single bottom-up weight for a motor neuron from a hidden neuron represents the likelihood that the connected hidden neuron fired, given that the motor neuron fired. It works similarly for our 9-column architecture, where hidden neurons that routinely fire at a given disparity are reliable inputs for their respective motor neurons, and thus their motor neurons have high weight values for them. However, what happens if there isn't enough information in a subwindow to get a specific disparity value? What happens if the subwindow has weak texture? Because some neuron has to win in each competition zone, some neuron has to learn weak texture. With volume dimension, all weak textures are made to be close to the same input, so only one neuron ever needs to learn the weak texture, helping the DN efficiently utilize its neuronal resources. This hidden neuron, which we call a noise neuron, can fire no matter what the actual disparity is, and therefore contributes equally to all motor neurons over time, as shown in this diagram. This equal contribution lowers the noise neurons and its respective columns' voting power to 0 when the noise neuron fires. The result of this is that the DN can detect weak textures and attend to those subwindows containing strong textures. The bottom-up weights for hidden neurons are important, but do not tell the whole story. The DN also uses top-down input. The top-down input acts as context for the DN, just as state match in a finite automaton acts as context for the FA. This state context gives the DN temporal processing ability, and in the context of stereo-disparity detection, helps the DN with its next disparity prediction by using its top-down weights to consider the lifetime history of top-down inputs and their relation to the next motor response. If the changes in disparity values are incremental, the top-down input lowers the probability of large disparity jumps in the response value. Jumping into our experiments and results, we will start with how we trained and tested the DN using the 3DI software. To help with training, testing, and all other interactions with the DN, we built the 3DI application. This image shows its graphical user interface. The two images overlap each other, left being purple, right being green. To maximize the amount of overlap at 0 disparity, we calibrate the image shift by choosing a point in the distance and aligning the left and right images on that point. This point then becomes the new 0 disparity and should be the average disparity as we train the DN. To label the disparity, the user must choose a point of interest in a part of the image within the green 3x3 that has strong texture. They must then align the two images using the controller that comes with the VCML100. For our experiments, we chose to always align on the nearest point. While they are continuously aligning the images, the application is collecting the images and their labels at a rate of 5 Hz. While the images and labels could have been fed directly into the DN, we collected them to run the DN on batch data so that we could experiment with different parameters. For our experiments, we collected one sequence containing 1,400 images and their labels from a natural setting. As I mentioned earlier, we always labeled on the nearest point with strong texture within the 3x3 mask. Once the data was collected, we went back through and checked the labels were correct, fixing any mistakes. We split the image sequence into 2 separate sequences by putting the odd frames in our training sequence and the even frames in our testing sequence. We then ran the DNs, varying the top-down weight between each run. The DNs we used had 100 neurons in each column, 900 neurons total, with top 8 competition performed in each column and top 3 competition performed within the motor area. To get the final result, we took a weighted sum of the top 3 motor neuron responses. And to measure the error, we measured the absolute difference between the predicted disparity and the actual labeled disparity. We ran the same set of tests on the GPU version to make sure the results matched and to test the speed difference. When we ran our experiment, we found that top-down helps, but too much actually hurts the performance accuracy. The best top-down weight seemed to be 0.1, which achieved an average error of 1 pixel. The graph shows the incrementally calculated average at any given test frame. It shows that top-down 0.1 did the best and top-down 0 did the worst, with an average approaching 2 pixels. We ran the experiment with the GPU version, and we achieved the exact same results, but obtained a significant speed up. The DN was able to update about 10 times per second while testing the GPU version, and it was only able to update 1 time per second while testing the CPU version. Our work presented the first developmental stereo-disparity detection system for real-world images. Developmental networks seem to be robust, real-time, and explainable solutions for stereo disparity detection tasks. Because they are general purpose, they seem to be great for making use of the rich information provided by a camera, which could help stereo cameras to compete with laser-based methods like LiDAR as the main sensor used to give autonomous systems spatial awareness. Future work will look further into how well the DN can perform stereo disparity detection by adding neurons, optimizing subwindow dimensions, optimizing neuronal growth rate, and varying the top K number. Future work will also look into how the DN can integrate monocular information with binocular information to perform more complex tasks. We hope to see this technology in use in the near future, making driverless cars and blind visual aids more adaptable. I'd like to quickly thank my co-authors on this paper for their great work. Fan Nam Hong for his work on the interface, Jacob Honer for his work on the visualization and data collection, Samuel Church for his work on the GPU version, and Dr. Tan Hai Tran and Dr. Jiang Wang for their mentorship on this project.